University of Warwick. We will talk about exponential decay of intersection volume and applications. Please welcome.
Hello. Yeah, thanks for the invitation. I'm glad to be here. I think, as most of you, last time I participated in workshop actually is also organized by DIMAC by Professor Sung Yeom last year around this time at Jeonju. That was quite nice. So, right. So this is the last day. So I try to make the talk easier so everyone can have a relaxing time. So this is a joint work, recent work. We post the paper today, so you can see on archive today. Exponential decay of intersection volume applications. This is joint work with Tuan Tran and Jae-Hoon Kim, who are both here. So if you have any questions, you can also ask them. So I remember when I was little, the advertisement is just very classical form. So we don't have this planned-in built-in advertisement. Nowadays, if I watch this Korean drama or other dramas, they will have this commodity showing up right in front in the screen, and you can see this advertisement. So I'm going to do the same. So we will have part 0 is a 20-second non-skippable advertisement. So I think you've seen this earlier. This we have. Where is it? Okay, so I will just say it by words. So we have this new group at IBS. I will be the new CI. So we're also hiring now. The deadline is January 14th. We will hire up to 5. So we welcome newly graduate PhD students or who's early in their career to apply. So, okay, so let's start the talk. The first part is a geometry 101. So when I talk about in the title, intersection volume, so let's start with a very basic classical fact in convex geometry. So the story here is that in part 1 is that in high dimension, things tends to be strange, very weird. So what do I mean by that? So we live in 3-dimensional Euclidean space. So let's look at in R3. If you take 2 balls in the picture here, we have a black one and a green one of the same radius, say. Whenever I say balls, they're identical ones. And let's say their centers are just a little bit apart, epsilon apart. And you take epsilon sufficiently small, it's easy calculation to show that these 2 balls, their overlap, the intersection volume highlighted here, is more than 80% or 90%, as long as you take epsilon small enough. Okay? This is quite intuitive, the space we live in. But then, when the dimension goes higher, actually the balls tends to be spikier than the smooth shape that we know. So what do I mean by that? So when we take n, which is the dimension, so now we're going to work in R3 instead of Rn, sufficiently large in terms of epsilon. Now again, you take these 2 balls of epsilon, the identical ones whose centers are epsilon distance away. As long as the dimension is large enough, you can actually guarantee the overlap is smaller than 1%. So they almost disjoint, okay? There's an easy proof. Let's see a proof. So basically, if you type in Wikipedia, what's the volume of the high-dimensional ball, this is the asymptotic of it. So the notation is that we live in n-dimensional Euclidean space with radius r, and the volume is roughly this expression. You can just forget about the first part, because what matters is that if we just consider n dimension, you consider 2 balls of different radius, let's say r prime and r, then the ratio of their volume in n dimension basically is their ratio of the radius raised to the power n, which is dimension. Okay? Now I can give you a very simple proof that the overlap is less than 1% as long as n is large enough. So here's the proof. Again, we have these 2 identical balls, the black one and the green one. Okay? And their centers, the black dot and the green dot, they're epsilon apart. So now I take the red dot, which is the center point of these two centers, the midpoint. Then the distance, of course, epsilon over 2. It's very easy to see that the intersection of these two balls is actually enclosed, completely contained inside this red one of radius r prime, which is strictly less than r. Let's say less than r minus epsilon over 10, just to be safe. Now, using this formula, we know that the ratio of their volume is r prime over r to the n, which tends to 0 as n goes to infinity. Okay? So it's very, it's not hard to see this. So there is a problem here of this approach. It's a very nice one, very simple. The problem is that this proof will fail at discrete setting. Okay? So let's see an example for this problem. So here's my example. Let's consider the discrete hypercube. So our space is binary strings of length n. And the metric we consider in this discrete metric space is the Hamming metric. So what is Hamming metric? Let's remind everyone. I will use big delta to denote the Hamming metric. Between two strings, let's say n equal to 3, their distance is basically the number of bits on which they differ. Okay, so on these two strings, they differ on the first two. Their Hamming distance is 2. So we consider this discrete metric space. Let's take some k and r such that k is at most r over 2, 2k is at most r. Now, again, I draw these two balls, A, the black one, center a little a, and B, the green one, center a little b. Since this is symmetric, it's highly symmetric, so I might as well assume A is the origin, all 0. I will denote by 0 to the n. And B, the green one, their distance is 2k apart in this picture. Okay? So I'll let it to be 1, 1, 1, 1, 1, the first 2k entry, and the rest is 0. Now, by symmetry, I can assume I can take a midpoint C, which is this first k entry 1, the rest 0. This is exactly in the middle of A and B. Now let's try to do the same as what we did in the continuous Euclidean space. Consider this purple point x. What's the problem here now? I take x to be 0 to the k, 1 to the r, 0 to the n minus k minus r. It's very easy to check that the Hamming distance of this purple x to both A and B is exactly r. So they are right at the boundary of these two balls. So they are in the intersection, right? But the distance of x to this midpoint C, you can compute, is r plus k, which is strictly bigger than the radius of the original ball. So then our original approach of bounding the intersection volume by the volume of a smaller ball will fail here because we have to take a larger radius. That's not okay. Okay, so this is part 1. Any questions? So to be continued. So let's move on to part 2. So part 2 is coding theory 101. Actually, I'm not an expert, so I can only do 101. So originally I prepared a video, but let's say we skip the video. So there's communication gap. So communication gap means in our daily, now it's a digital era. We use a cell phone, right? When we're sending these messages, we have to send wirelessly, and there's noises, right, by say, magnetic field or this kind of thing. So sometimes the bits, the binary bits, they send over or get flipped to the opposite bits, right? Then there's this error. Then what do we do? There's this so-called error correction code they come to rescue. Okay, here's an example. The idea basically is that we want to encode the messages so that they are pairwise far apart. Then the receiver, when they receive the message, there's no confusion, right? So let's see a simple example. Usually people do Alice and Bob, but since we're in Korea, so let's do Soyeon and Ji-Woon, okay? So these two people, they want to send messages to each other, right? It's very simple example. Let's say we use 6-bit binary string to encode the message. There's only two. Say Ji-Woon asks Soyeon a question, and he wants to know this answer is yes or no. And let's say the noise is up to 2 bits. Any 2 bits, up to 2 bits can get flipped. Okay, then we want to know the answer. As long as we can encode this yes and no far apart, so let's say we use this 0, 0, 0, 1, 0, 0 to represent yes, and all 1 to represent no. Let's say at the receiving end, we get this string. Now all we need to know to decode is to see the Hamming distance of the receiving string to these 2 representing strings. Okay, it's easy to compute the distance, 2 and 3. Then we know that it has to be yes, because we agree beforehand the number of bits the noise can corrupt the message. Okay, so in general, here's a picture, maybe more general picture, is that we have this space. It could be a Hamming space over larger alphabet. Doesn't have to be 0, 1 to the end. The idea is that we use these. The code words are these red crosses. We want these red crosses, the messages, to be pairwise far apart. Let's say distance more than d apart. Then as long as the noise can corrupt at most d over 2 bits, then there will be no confusion. Whatever message we receive at the receiving end must fall into the vicinity of one of these crosswords, right? There's no overlap. So we just find the closest message, then we can decode it. Okay? Then the central problem in this error correction code is how many messages we can send. We want to do things efficiently, economically. So let's formalize it a little bit. We define capital A of n and d to be the maximum number of code words or messages we can send through n bits binary string, as such that condition on their pairwise Hamming distance is at least d apart. Okay? Then it's safe to say that the best known lower bound so far, apart from the lower order improvement, is still about 70 years ago given by Gilbert Warschaman, this very classical bound. So what is this bound? It says that we can guarantee that the maximum size we can send over on the binary case 2 to the n over the volume of this n-dimension ball of radius d. This is the classical Gilbert-Warschaman bound. So why don't we see a proof of this? It's very easy to prove. And then when you see the proof, you will be surprised that there's no improvement over this very simple proof. Okay? So here's the proof. So first of all, let me remind you that simple combinatorics compute the volume of this n-dimensional radius d ball. What is it? Basically, you fix your string, n bits. How do you go radius d? You choose your d up to d coordinate, n choose I goes from 0 to d, and you flip the bits. Okay? So in your radius d ball, you have this many messages, this many strings. So here's the proof. What we do is we're going to take, so this is our space. Here's the picture. We take a maximal size code. Maximal means maximum under inclusion. You cannot make it bigger. The first step is simple. Now what do? These are the red crosses here, okay? And these little red balls are the radius d over 2 that we drew before. They has to be disjoint because of their pairwise distance strictly bigger than d, okay? Now what I'm going to do is I'm going to double the size of this red ball from radius d over 2 to radius d, which is this green ball. What's the key observation here? The whole space, 0, 1 to the n, must now be covered by the union of this double-sized ball, the green ones. Why? If not, then that means there's a space to add another point here, right? But what does this other point mean? This new point will necessarily be out of all these green balls, meaning that it is of distance d, more than d away from all the existing ones. So that means we can add more code words. We can add more messages, contradicting to the maximality of the original code that we take, okay? And that's the proof. The rest is simple arithmetic. So what we have is this computation here. We have the whole space, 2 to the c, is covered by the number of messages times the volume of this green ball. Okay? Then you flip you solve this inequality, we get the Gilbert-Wassermann bound. It's basically two-line proof. And surprisingly, this stands there, at least for the base of the exponents. So there's I will skip the literature. Basically, the upper bound also comes from this kind of volume argument, because the radius d over 2 ball are disjoint. So they are disjoint, their union must be smaller than the volume of the whole space, then you can do that. So there's this big exponential gap. And it's a major open problem to improve or to close this exponential gap between the upper and lower bounds. Okay? Good. So this is also some very classical stuff to be continued. So let's look at part 3. Actually, I started with extremal graph theory. So extremal graph theory 101, we've seen some of the talks here mention the name of Turan. So we also see Turan's theorem, but in a slightly different form. But I will start with this puzzle. Okay, let's do a little game here. Let's say we want to pick, for your choice, to pick n numbers, say x1, x2 to xn. Okay, you can pick whatever real number you want. Well, actually, irrational numbers. You have to pick irrational numbers, but you can pick whatever irrational numbers you want. What is the goal then? The goal, your goal is to try to maximize the number of so-called rational pairs. Okay? By rational pair, I just mean the pair. You want to maximize the number of xi, xj pairs such that their sum is rational. Okay? Even though each individual one is irrational, you want to maximize the pair whose sum is rational. Simple game. The question is, how many pairs you can get? What's the maximum number of pairs you can get? Given n, say n is a large number. Okay? Yes, here's a little puzzle. Anyone know the answer?
Probably n squared over 4.
N squared. We will see why it's n squared over 4. Okay, that's the correct answer, right? So actually, this is a toy model of a more classic, very classical problem called Turan problem. So let's look at this Turan problem. Summarized in a very easy way, succinct way, is that our task is we have a graph, given number of vertices. We want to maximize the size of it, i.e. the number of edges in the graph. Okay, that's what we want to do. But we have to restrict ourselves into a particular class of graphs. So we usually look at H-free graphs, so meaning that we're going to forbid some substructure H. And here, forbidding substructure is not necessarily as an induced subgraph. Okay, so slightly different from some of the previous talk where we ask for inducedness. And we don't ask for that. So here's a tiny example. We have this graph G like a house. And we have F and H. F is a full cycle. H is a full cycle with a diagonal chord. Then we say F embeds into G. So this is a subgraph of G. But G is H-free. That's a very simple example. Straightforward to see the definition. But a little bit cumbersome to write it down. So then the puzzle that I gave you before is actually basically answered by this very classical theorem more than 100 years ago by Mantel, 1907, who proved that the most basic case of this Turan problem, what is the simplest graph you can come up with to forbid? The triangle, right? The 3-vertex complete graph. So he says that if you have an m-vertex graph, let me move this, yeah. If you have an m-vertex graph that is triangle-free, then the maximum number of edges you can have is n squared over 4. This bound is tight because we can partition the graph into 2 parts, left and right, almost equal size. Let's say n is even, and you only add edges going across 2 different parts, and leave left side and right side to be empty without any edges. So there's no triangle. and number equality is attained here, okay? Coming back to the puzzle, we can build an auxiliary graph. If you choose endpoints, we can build an auxiliary graph to one vertex for each irrational number that you pick, and you put the edge in this auxiliary graph if they form a rational pair, right? So then in this question, it's easy to see that this auxiliary graph has to be triangle-free. You cannot have three numbers, each one of which is irrational, but their sum pairwise are all rational. That's impossible, okay? And this upper bound is attainable just by complete bipartite graph. So your choice can be, you can take left side to be some Si plus root 2, and right side to be some T sub j minus root 2, right? And everything going across this root 2 will get canceled out. Si, Tj, they are all rational numbers, okay? So each one of them is irrational, but the cross sums, they are all rational. So this is a tiny example showing the tightness. Any questions? I think someone tried to look up this reference and they have some trouble. I actually didn't look up, so it just show up everywhere. So later, this theorem got generalized by Turan. So this is why nowadays we call this Turan type problem, because instead of triangle free, so triangle we also call it complete graph because all the edges are present in such a graph. So triangle is a complete graph on 3 vertices. Turan is considering forbidding a larger complete graph or clique. So you forbid, say, 4 vertex complete graph or 5 vertex for any fixed size clique. And then he obtained a tight bound. So I want to tell you this Turan theorem, but rephrase a little bit, slightly different from Mantel's theorem, the way we phrase it, because we're going to use it in a different way later. So basically, we're going to take a Mantel's Turan's theorem and take the complement, okay? So a small piece of notation. We define these independent sets in the graph. What is it? It's very simple. It's just basically a set of vertices, S. It's called independent set, highlighted in red here, if you don't see any edges when you zoom in there, okay? So these 3 vertices, they form independent sets. So Turan generalized Mantel's theorem. If we take the complement of this statement, this will be this statement here in the green. It says that if we have an n vertex graph, I take a special case actually to make things simpler. N vertex graph that is d-regular, meaning that every vertex is adjacent to d edges, okay? Then the independence number, that means the size of the largest such independent set, is bounded from below by the number of vertices n divided by the degree d plus 1. Okay? A very classical bound. And this bound, you cannot improve it. This is tight in general, as shown by this example here. G, our host graph, n vertex graph, could just be unions of clique, complete graph kd plus 1. This is easy to see that it's d-regular. Every vertex leaving complete graph d plus 1. And the largest independent set, you cannot take 2 vertices from the same clique because they are adjacent. So you can only take 1 vertex from each one of them. You get n over d plus 1. Equality holds. We cannot improve it even by plus 1. Okay? But sometimes in extremal combinatorics, what we do, or even in other branch of mathematics, when the theorem is tight, what you're going to do is say, okay, you look at the tight example. If you say you want to step away from such tight example, can you improve it, right? It's a very classical theme, a meta problem. So we can do the same here. If you look at this red example, in particular, it has lots of small cliques or triangles. So we can improve it indeed. This is a classical theorem in the 80s by Aitai, Komlos, and Samaredi, where they proved that if our graph is triangle-free, so for example, this graph has lots of triangle, then we can improve it asymptotically by a log factor in D, which is the degree. So here, let's just look at asymptotic now. This is roughly n over d up to constant. And what they're saying is that if you're triangle free, then you can do n over d times log d up to some constant. I will not prove this, but this is not something that we need actually. We will use something slightly stronger than that. You can even get this log d factor improvement if your graph is not triangle free but locally sparse. Roughly speaking, what does it mean locally sparse? Here's a picture illustrating it. Informally, it means that the neighborhood of every vertex in the graph spans a very sparse graph, informally speaking. Okay? So here's a picture. You look at any vertex v, but usually we consider vertex transitive graph. So the neighborhood of any vertexes, they all look the same. So you look at n of v, which I denote the neighborhood. We want this red part to be, there's not so many edges in there. Okay? Any questions? So we've seen 3 parts, seemingly irrelevant, right? We have this intersection volume, this high dimensional ball, and we have this error correction code. And at the end, we're talking about this, the Turan's theorem about independence number. So let's see how they all come together, the final parts. The first thing I want to show you is that the cornerstone theorem, Gilbert-Wassermann bound in error correction code proved in the 50s, is actually equivalent to Turan's theorem, the main theorem in extremal graph theory. They are exactly the same. So how do we prove that? Let's recall these 2 statements. Gilbert-Wassermann bound says the simplest case, we have binary string of length n, so the whole space is 2 to the n size. It says that if you take a collection of binary string of length n, pairwise distance at least d plus 1, then it's at least 2 to the n over the volume of the radius d ball. Okay? We've seen this. This is the same as Turan's theorem, saying that if you take a capital N vertex graph that's d regular, every vertex of degree d, then independence number is at least n over d plus 1. Why? We build an auxiliary graph, G, where the vertex set of the auxiliary graph is all the length n binary string. Okay? So we're going to encode this into an auxiliary graph. What are the edges in this graph? We put an edge in the graph. X and Y are 2 length n binary strings. We put an edge if their Hamming distance is the most d. Okay? Now, what's the key observation here? What's the point of this auxiliary graph? The point is that any encode here, a collection of binary string of distance at least d plus 1, strictly beyond d, correspond to the independence set in the graph, in this auxiliary graph, right? Recall, what is independence set? A set of vertices where there's no edge. What does it mean, no edge? That means their distance is strictly bigger than d. That's how we put an edge, right? Good. Then, Turan's theorem says the independence number, which now gives you a lower bound on the size of the code, is at least the number of vertices, which is 2 to the n, up here. These 2 are the same, divided by the degree plus 1. What is degree? Every vertex, every message is adjacent to all the strings that's of distance d from it, apart from itself, minus 1. Okay? So these 2 are exactly the same. Any questions? One-sided, okay. What I mean exactly the same means Turan's theorem actually implies Gilbert-Wassermann, yes. Okay? Good. But we've only so far made the connection between part 2 and part 3, right? The codes and the independence number. Where does this intersection volume come from, right? It seems to be still irrelevant. So how does intersection volume kick in? So the intersection volume kick in, recall this I-type comotion similarity theorem that I mentioned earlier. that even though Turan theorem is tight, N over D asymptotically is best possible, but you can give improvement, a log D improvement, when the graph is locally sparse. Okay? So the idea here is that we're going to use the decay, these two balls, their intersection volume, decay in high dimension, to show that certain auxiliary graph that we built, like the one we built earlier, they are locally sparse. So if we can do this, then we can get this log D improvement. Okay? That's the idea here. One of the punchline. So let me illustrate a little bit. What do I mean? Decay of the intersection volume implies locally sparse. Recall this graph that we built, where the vertex is the binary string, 0, 1 to the n, and two are adjacent if their distance is most d. Then what we want to show locally sparse means in the neighborhood, if you take a vertex x, what is this neighborhood, n of x? It's precisely the ball of radius d around this string x, right? We put an edge if their distance is most d. That's precisely the ball. Then locally sparseness, what we have to show is all the vertices of the string y inside this ball, inside the neighborhood, they will have low degree in the neighborhood n of x. Okay? Actually, I cheated a little bit here. Not necessarily this is always true, because if you take y super close to x, then the degree of y is almost the whole n of x. But we actually cared about a typical y here. So let's say we take a typical neighbor y inside the neighborhood. Then what is the degree of y inside the neighborhood x? Is precisely the intersection volume, if you think of it. Right? So two are adjacent if the distance is most d. So y, their intersection volume here is the co-degree of x and y, which is precisely the degree of y inside the neighborhood of x. So now small intersection volume, if we can prove it, will implies locally sparseness. Then we use this some variant of I-type Combinatorics similarity. We can improve this Gilbert-Wassermann bound by a lower order term, which is logarithmic in the degree. Any questions on this part? Then that brings us to the main task. How do we bound the intersection volume? So we back to this geometry, the combinatorial geometry problem. Okay, in the discrete setting, how do we bound the intersection volume? That's the part one we begin with. We've mentioned that we cannot use this continuous setting idea of using a smaller radius ball to bound the intersection. So now we propose to do things differently. We're going to bound the intersection probabilistically, okay, while concentration of measure. So what is our goal? Let's recall our setup. Forget about all the code, all the extremal graph theory. All we need to do now is a geometric problem. We have two balls in the discrete metric space. Let's say 0, 1 to the n. We have two balls of same radius. Center at A, the black one. Center at B, the green one. Their distance is, say, k apart, and their radius is little r. Our goal is to prove that the volume of their intersection, A intercept B, the ratio with respect to the volume of A, the original ball, decays exponentially, where the exponential is in terms of the distance between their center. Okay? That's the original setup. You can forget about everything I mentioned before now. So how do we interpret this thing, this intersection volume ratio probabilistically? It's actually not hard to write it. So what we're going to do is to sample a random point x inside, say, the left ball A uniformly. You take a uniform point. Then what is the probability that a uniform point on the black ball falls into the intersection A intercept B? That's precisely the ratio of the intersection with respect to A. Okay? Probability 101. Now, what we're going to do is to do a concentration of measure. to carry things through. So I'm going to do things again informally, hiding some technicality. Let's recall this picture, and we have this proof in one page, omitting some technical stuff. So here's our setup. 2 balls, black and green one, distance k apart, their center, radius r. We want to bound the probability that the uniform sample point x in A falls into the intersection A and B. That's what we want to do. So basically, our theorem is stated as giving natural sufficient conditions guaranteeing this exponential decay of the intersection volume. So our condition says, as long as you have certain growth, the space, the metric space enjoys some certain growth, meaning that if you center at a point and look at the ball grow bigger and bigger, it grows quite fast, let's say exponentially with respect to the radius. This is very natural. Just consider the Euclidean space we mentioned earlier. The ball grows exponentially in terms of the radius, right? Assuming this natural condition, then what we know is that the mass of the ball A is highly concentrated on its boundary, the shell, right? Then we can kind of condition actually our random variable x, the uniform random point, to be on the shell, the red dotted line. Okay, we can pretend that it's not uniformly sampled in A, but uniformly sampled at the boundary of A. Let's do one assumption, do this conditioning. Then the second thing we have to assume about the metric space is some sort of well-spreadness. So the space is the elements of this discrete metric space is uniformly distributed. What does it mean? That means basically this inequality. If we condition on x leaving out the boundary of A, what is the expectation of the distance of this uniformly sampled x on the boundary to the center of the other ball, little b? Okay? Just imagine Euclidean space. If we sample this in the Euclidean ball, then you can kind of intuitively see that Euclidean space are very uniform. So this x, most of the time, is more than r away from B, right? It's outside of the green ball. And by some margin, which is some term, linear in k, which is the distance between them. This seems also intuitive to imagine. And it's not hard to verify for different kind of discrete metric space, such property. Assuming this, now what's the point here? The point is that this random variable induced by x, the metric, the distance between x and b, is a Lipschitz function. It varies smoothly on the entry of each coordinate. Then we can use some sort of concentrational measure, but on the slice. Here, on the slice, I mean x is not uniformly distributed over some space, but over some particular space conditioned on something. Here, we're conditioning on the shell. That's what I mean on the slice. Then you can show that with high probability, because the expectation, the distance is r plus ck, then with high probability, it's actually strictly more than r away from B. Okay, the distance. But what does this mean? The distance strictly more than r away, that means x is not in B, not in the green ball. So what we have just shown is that under these 3 green condition, the natural condition, boom, 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 then with high probability, x does not lie in the intersection A and B. Translated back, that means the intersection volume has to be very tiny. Okay? So a summary of what we talk about. So as I said, our main theorem is this. Our main theorem says we give some natural sufficient conditions, these 3 conditions. The metric space enjoys some growth and is some sort of uniform. The points are nicely distributed. And then we have to prove some concentration, large deviation inequality for some Lipschitz functions that's distributed over certain space, subspace of a space. Okay, then we can guarantee, you can plug in here to guarantee a small intersection volume of identical balls. All right, that's our main theorem in an informal way. The application, which I will not have time to talk, just to summarize in this slide, is we use this intersection volume to give, for example, optimality of list decoding capacity theorem, which was conjectured by Lee and Wouters. And then we also give improvement asymptotically linear in the dimension of this classical bound by Levenstein on constant weight code. And such improvement was also asked by John and Vardy in early 2000. This also gives a unified framework. This is the part that we talk about, the error correction code, of improving this Gilbert-Wassermann type bound. So it's quite general, so it can be applied to different kind of discrete metric space. You can enlarge the alphabet from 0, 1 to, say, quinary. Or you can even replace the base sets by the set of permutations on ground set n, 1 to n. Again, using Hamming metric. This is called the permutation code. And this idea, even though not directly applicable, but it's amenable to a continuous case, the spherical codes, which are unit vectors that are every pair of which their angle is at least some certain degree apart. Okay, so you can get some improvement over this. For example, in particular, this spherical code, this improvement is only very recently made after 50 years. And under our framework, the proof is very simple. It's just half page, assuming all previous main results. Okay, so there will be. I will end the talk a little bit earlier, so we can have some coffee. Any questions?
Any questions?
I have one question. So, is there any algorithm to achieving your lower bound to find the lower bound of the independence number in your setting? Yeah.
Okay. I think there's some algorithmic results, but not from our result, because most of the time we just prove the existence of the independent sample by size. One classical way, for example, recently, one way of doing it is to use this Poisson process with some condition. It's a classical way of doing things in statistical mechanics. Then this random probabilistic proof basically give a low bound independence number. If you do it that way, you can only prove its existence. But there are some algorithmic ones. I cannot recall off the top of my head. Any other questions?
You have this constant C in front of this n number E log D.
Yeah.
So in order to beat the current bound, I mean, perhaps your C must be small, right? Very small. Yeah, that's C.
Right.
And so to beat the current bound, you need the n to be large, right?
Yes. Right.
So how, for the applications, perhaps the n is not predict for coding theory. So I wonder how big the n should be in order to beat the current bound.
Yeah. This is we have to define what mathematicians means application. So very much on the paper. Yeah. So n has to be large. So I didn't do the calculation, but as you said, it's not practical, I would say.
I see.
It's
How
more
small
like
is
theoretical.
it?
The C is actually reasonable, assuming you're locally sparse. So if you look at a completely random graph, the number of triangles you would expect is roughly degree cube, d to the 3, right? Because if you uniformly random sample 3 points, you have n cubed number of choice, and the probability they form a triangle is p cubed. So n cubed, p cubed, which is degree to the power 3, okay? Then this locally sparseness says that as long as you are degree to the 3 minus some constants, then you can have this constant C, something like 1/8 of 1, actually. Yeah. So it's a very reasonable constant. Maybe 1, I think. 1 minus 8 over 1.
Any other questions?
Yes?
So the result you described, the Turan's theorem implying this classic
Actually, no. So since this is proved in the 50s, right? But then this connection is only seen in early 2000. That's after 50 years. Well, now from today, it's 20 years ago. That's quite a while. People noticed that in these two literature, this theory implies the basic one here implies the
Yeah, so my question is, have you said that your key contribution might be the latter part of the measure concentration?
Yeah, that's the title of my talk is about proving the exponential decay of the intersection volume. Yes.
Any other questions?
So, you building an auxiliary graph from your discrete setting. So, is there any known structure like something minor free or some bounded width parameter for that auxiliary graph?
That's actually a very interesting question. So, as I said, one of the major overwhelming error correction hope is to improve the exponential constants between lower and upper bound. If you have a rational bound, and I think the upper bound has singleton bound or Hamming bound, the upper bound, there's a big exponential constant. Which, if I translate into graph language, what you want to do is to prove some bound on dependence number roughly look like n over d to the 0.99 instead of n over d. Okay, you want to improve the power of d. Then there is actually some normal result factor assuming it will be some small clique as minor. You can do n over d to the 0.99. But the problem is, how do you translate it back? I actually thought a little bit of this, but this a lot of natural model of this code there they have large clique as minor. So it's not directly, it doesn't directly translate back to some common ones. So this is something to think about. If there's some other natural conditions to impose on graphs, so that you can improve this bound or independence number by you save some power saving power. Then you will, the hope is to get some special class of codes on which you can beat the Gilbert-Rushing bound exponentially. Okay.
Any other questions? If not, let's thank our speakers.
I would like to thank to organizers. They allowed me to speak in Korean. I prepared my presentation slides in English, so don't worry. And you can ask in English or in Korean anyway. 제가 이걸 한국말로 준비한 이유가 좀 특별하게 있습니다. 그래서 저는 지금 이제 국가수리과학연구소 산업수학혁신센터에 있으면서 조금 특별한 일을 하고 있어서 코로나 시대에 조합론 하는 선생님들 그리고 영스칼라들을 꼭 만나서 제 문제를 좀 이야기를 해주고 싶었어요. 그런데 참 코로나 때문에 만나기가 힘들었는데 그래서 이 기회에 저에게 주어진 25분 동안 최대한 많은 것을 어필해가지고 여러분들에게 뭔가를 받아내기 위해서는 어쩔 수 없이 한국말로 할 수밖에 없었습니다. 이해해 주시기 바랍니다. 그래서 제가 이제 산업수학혁신센터에 있는데 그래서 ICIM이라고 적어놓았습니다. Innovation Center for Industrial Mathematics라고 저희가 이제 지금 현재는 2016년에 저희가 판교에서 시작을 했고 현재는 광교 수원에 있는 광교에 지금 있습니다. 제가 생각하는 산업수학은 뭔가 하면 여기 적혀 있는 것과 마찬가지로 인더스트리얼 매스매틱스가 아니고 Math for Industry입니다. 그래서 제가 생각하는 산업수학은 이 현장에 있는 문제를 Real World Problem을 Mathematical Way로 그러니까 수학적인 방법으로 좀 풀어보자 이렇게 해서 지금 주창하면서 시작을 했고 지금 현재까지 오고 있는데 많은 기업에서 의뢰하는 문제들은 결국은 뭔가 하면 크게 두 가지입니다. 요즘 화두가 되는 AI 아니면 뭔가 하면 옵티마이제이션 프로블럼입니다. 철저하게 옵티마이제이션 프로블럼. 그럼 현재 제가 오늘 던지는 문제도 옵티마이제이션 프로블럼입니다. 보셨죠, 그죠? 뭐 사용하고 계시는 분도 있을 거고 이마트나 어느 마트에 가도 글라스락은 항상 있으니까 글라스락 이사님이 직원들을 데리고 저희 센터를 방문했어요. 언제 올해 봄인가 쯤에 방문해서 뭘 원했는가 하면 자기들이 글라스락이 뭔가 하면 저 유리로 된 컨테이너인데 261개의 글라스락 컨테이너를 가지고 있는데 현재 시판하고 있는 게 전부 랭스, 위스, 하이트가 다 다르다. 자, 그리고 자기들은 이걸 이제 딜리버리하기 위해서 자기들은 그러니까 소매점에 판매하는 정도뿐만이 아니고 해외 수출도 엄청나게 많이 한다. 그래서 자기들이 사용하고 있는 박스, 이 사람들은 박스라고 부르지 않더라고요. 카톤이라고 부르더라고요. 카톤. 그래서 111개의 서로 다른 카톤을 사용해서 그리고 박스 디바이더가 이거 한국말로는 이 사람들은 용어가 업계 용어는 사절입니다. 사절. 박스 디바이더 그리고 레이어 패드는 이거 위로 이렇게 까는 패드. 그건 패드라고 보통 부르던데 이걸 이용해서 커다란 박스를 크다랗다기보다도 이제 자기들이 쓰는 111개의 스탠다드 카톤이 랭스와 위스와 하이트가 저런 식으로 111개를 지금 사용하고 있대요. 근데 문제는 뭔가 하면 박스가 너무 종류가 많아서 돈이 많이 든다. 박스 제작하는데 돈이 많이 든다. 그래서 어떻게 하면 당연히 문제가 뭐겠어요? 박스의 개수를 좀 줄이는데 아까 봤던 260개의 컨테이너 글라스락 유리 컨테이너들을 전부 다 담을 수 있는 그런 박스를 어떻게 제작할 수 없겠느냐? 몇 개 정도면 되겠느냐? 그래서 문제는 뭔가 하면 111개가 전부 다 커버를 못하니까 원하는 문제는 옵티멀 넘버를 좀 알려달라. 뭔가 하면 이 사람들이 원하는 컨스트레인트는 1, 2, 3밖에 없습니다. 첫째, 하나의 박스에는 하나의 컨테이너만 들어가지 여러 개 안 들어간다. 절대 안 들어간다. 한 개만 들어간다. 두 번째, 이 사이즈는 카톤 아까 봤던 그 스탠다드 카톤 사이즈 안에서 골라야 되지 그걸 더 크게 하고 더 적게 하는 건 안 된다. 그 안에서만 아니라. 그다음 세 번째, 마진이 남는 여백이 위스와 그리고 랭스 쪽에서는 한 5mm 정도 수준으로 하면 뭔가를 더 뗄 수 있다는 거죠. 그리고 하이트 쪽에는 한 2mm에서 그 패드, 레이어 패드를 붙일 수 있는 이 정도 수준으로 허용을 하겠다. 그리고 나서 저희가 물어봤죠. 보통 이건 이제 컨스트레인트는 다 줬으니까 그러면 오브젝티브는 뭐냐고. 뭘 원하시냐고. 옵티마이제이션 해야 되니까 뭘 원하냐고. 원하는 게 없대요. 아주 땡큐인데 원하는 게 없다. 그래서 그러면 할만하다. 원하는 게 없으니까. 그래서 저희 센터에서 준비한 게 첫 번째 카톤 캔디데이트를 이제 쭉 잡아봤습니다. 저기가 이제 235mm부터 645mm까지 랭스를 5mm 단위로 자르고 그다음에 위스도 자르고 하이트도 쭉 잘라가지고 랭스가 위스보다 큰 것들만 전부 골라봤어요. 그러니까 총 386,346개의 카톤 캔디데이트가 나오죠. 그래서 우리는 뭘 만들 수 있는가 하면 매트릭스를 만들 수 있습니다. A 매트릭스라는 걸 만들 수 있는데 A 매트릭스에 로우는 몇 개인가 하면 38만 개가 있고 그다음에 261개의 컨테이너 유리 용기를 다 채워야 하니까 261개의 칼럼이 있다고 생각해 보자고요. 그러면 주어진 저 박스가 이 주어진 카톤을 전부 다 담을 수 있는지 안 담을 수 있는지 그걸로 마진 안에서 그러면 true or false가 딱 나오죠. 그래서 true or false를 가지고 있는 value를 true or false를 가지고 있는 우리가 커다란 매트릭스를 만들 수 있다고요. 그러면 답은 뭔가 하면 이 중에서 feasible solution이 A에서 low를 몇 개든지 잡아내는데 단 어떻게 돼요? low의 칼럼들의 썸이 1보다 크면 되는 거죠. 아주 간단한 문제라고요. 그래서 이게 보면 38만 개가 있다고 쭉 이렇게 해서 로우가 있는데 결국 듀플리케이트 로우가 너무 많기 때문에 다 날려보니까 결국 몇 개가 남는가? 319개밖에 안 남아요. 그러면 이제 아주 손쉽게 풀 수 있는 거죠. 그래서 이건 뭐 크게 뭐 손으로 할 수는 없고 저희가 이제 보통 이제 쓰는 게 CSP 프로블럼으로 생각해가지고 MIP 솔브를 돌리거나 아니면 구글 OR 툴즈에 있는 SAT 솔브 이런 것들을 이용해가지고 금방 우리가 답을 얻을 수 있습니다. 근데 아쉽죠. 그러니까 저쪽에서 제가 이제 정말 오브젝티브가 없느냐, 옵티마이제이션을 위한, 틀림없이 당신들이 이런 걸 원할 건데, 그러니까 이게 뭔가 하면 팔레트입니다. 이걸 팔레트라 그러는데, 이거 보셨잖아요. 뭐 기계 이렇게 쭉 가다가 딱 이렇게 올려가지고 이렇게 하는 거. 이 팔레트 위에 이런 식으로 쌓진 않고 보통 이 박스들을 이렇게 쌓는데 동일한 형태로 이렇게 쌓더라고요. 왜 쌓는가 하면 이렇게 쌓고 나서 비닐로 확 덮어버려요. 그리고 꽁꽁 묶어버리기 때문에 이 위로는 동일하게 가도 별 상관없습니다. 이런 식으로 해서 해외 수출하고 이렇게 한대요. 그러면 저희가 제시했는 게, 그러면 당연히 이 팔레트 위에 박스가 많이 들어가는 게 좋지 않냐. 이런 옵티마이즈 오브젝티브를 거는 게 좋지 않겠냐니까 필요 없대요. 왜 필요 없는가 하면 복잡한 걸 주면 작업하는 사람들이 외울 수가 없다는 거예요. 그 사람들은 그 사람들의 스킬이 있기 때문에 그 사람들의 스킬대로 놓는 것뿐이지 괜히 알려주려고 하지 마라. 그게 현실입니다. 그래서 오케이. 그래서 이 문제는 간단하게 끝났는데 제가 이제부터 관심이 있었죠. 그렇다면 이 팔레트 위에 저런 박스들을 놓았을 때 어떤 게 있느냐 한번 생각을 해봤죠. 그러니까 온라인 팔레트 로드라는 어떤 사이트가 있더라고요. 이 사이트에는 우리가 위스, 랭스, 하이트를 주고 그리고 나서 뭐 이런 식으로 데이터를 주면 보통 한국에서 주로 쓰는 이 팔레트 사이즈가 1200에 1000인데 그러면 도대체 몇 개를 옵티멀하게 놓을 수 있는지 이걸 가르쳐 줍니다. 그림으로. 한번 여러분들도 저 사이트에 가서 한번 보시면 복잡한 것은 아주 복잡하게 나와요. 그래서 이제부터는 제 관심이죠. 한번 찾아봤어요. 이게 뭐가 아까 봤던 박스가 저 팔레트 위에 얼마나 많이 놓여질 수 있느냐. 그래서 여기 있는 레퍼런스가 2016년에 나온 좋은 그 서베이 논문입니다. 그래서 이걸 토대로 해서 잠시 프로블럼을 설명드리겠습니다. 이걸 Manufacturers Pallet Loading Problem의 MPLP라고 그러는데 아주 간단한 거예요. 뭔가 하면 the problem consists of 뭘 놓는가 하면 박스를 카톤을 놓는데 전부 동일해야 됩니다. 아이덴티컬 렉탱글을. 팔레트도 고정된 하나예요. 하나 위에 몇 개를 놓느냐, 맥시멈 넘버가 몇이냐를 알고 싶은 거예요. 아주 단순합니다. 대신 조건이 뭔가 하면 여러분도 예상하시겠지만은 첫 번째 45도 기울이고 이런 거 안 된다는 거예요. 무조건 정방향으로 놓든지 아니면 90도 돌리든지 두 개밖에 안 된다. 그리고 절대 당연하죠, 그죠? 오버랩 돼서는 안 된다. 이거밖에 없어요. 달랑이거다. 대신 우리가 아까 봤듯이 이 레이어로 계속 올리기 때문에 2디멘셔널 프로블럼으로 당연히 생각할 수 있다. 그래서 언뜻 봐서는 그 냅색 프로블럼하고도 좀 비슷하고 그렇게 볼 수도 있고 2디멘셔널한 뭐 그런 것도 볼 수 있고 있는데 이게 생각보다 오랫동안 연구를 해왔더라고요. 그래서 당연히 이런 산업공학 문제, 그러니까 오퍼레이션 리서치 문제들은 리니어 프로그래밍 모델로서 다루는 게 일반적입니다. 여기에 익숙하지 않은 사람들은 약간 그렇겠지만 그래서 리니어 프로그래밍 모델은 간단하게 어떻게 되는가 하면 이 베리어블들을 지정해 주는데 어떻게 지정해 주는가 하면 여기에 상자가 놓이게 되면 놓일 수 있을까 없을까 베리어블로 다 만들어 준다고요. 돌려서 놓을까 그냥 놓을까 이런 식으로. 그리고 나서 컨스트레인트를 어떤 식으로 주는가 하면 이런 식으로 만약에 저기에 상자가 놓이게 되면 까만 점들은 오버랩돼서 다른 상자가 놓이면 안 되죠. 그런 컨스트레인트 조건을 주는 거예요. 그리고 나서 저 ILP 프로블럼을 옵티마이제이션 프로블럼을 그냥 이렇게 푸는 겁니다. 그래서 이건 뭐 산업공학에서 주로 쓰는 것이기 때문에 여러분들이 뭐 그렇게까지 관심 있으신 분들은 보시면 되는 거고. 그래서 문제가 뭔가 하면 너무 베리어블들이 많기 때문에 이걸 풀기가 힘들어요. 사이즈가 크면. 그래서 이 사람들이 쓰는 게 최근에 2010년에 나온 저 리커시브 파티셔닝 알고리즘이 어떻게 보면 제일 좋다라고 이야기하는데 어느 정도 수준인가 하면 이 98,000개의 저 카바셋이 일십100, 1000만, 10만, 70만 초 안에 며칠 걸리죠. 저 정도. 그러니까 이 정도 안에 푸는 게 현재의 소타 알고리즘입니다. 근데 제가 지금 여기서 이야기하고 싶은 건 뭔가 하면 이제 한 10분 정도밖에 시간이 없기 때문에 이제부터 수학으로 들어가야 되는데 결국 이 문제는 뭘로 생각해 볼 수 있는가 하면 이제 파티션 문제로 생각해 볼 수 있다는 게 예전 80년대부터 알려져 있어요. 근데 보면 가정을 어떻게 하는가 하면 모든 박스들을 왼쪽으로 다 밀고 그다음에 아래로 다 민다고 생각하면 이 코너들이 전부 다 뭐로 나오는가 하면 A와 이걸 그러니까 팔레트의 랭스를 L이라고 하고 그다음에 팔레트의 위스를 W라고 라지 W라고 하고 박스가 AB라고 하자고요. 그러면 A와 B의 난네가티브 리니어 콤비네이션으로 다 나타난다고요. 그래서 이게 키포인트입니다. 어떻게 보면. 그래서 feasible 솔루션이 뭔가 하면 feasible 파티션이 뭔가 하면 이러한 S라는 게 L 또는 W가 주어졌을 때 이거보다 작거나 같은 모든 난네가티브 콤비네이션들을 다 모아놓은 거. 예를 들어서 이걸 보자고요. 22, 16, 5, 3 이러면 만약에 L을 잡으면 22를 잡으면 이렇게 나오겠죠, 그죠? 이건 이제 feasible 솔루션을 feasible 파티션이라고 부르고. 근데 사실 이런 feasible 파티션은 어떻게 보면 되는가 하면 A 쪽으로 박스가 하나도 안 들어가고 B 쪽으로만 세워졌을 때 몇 개 들어가느냐 이걸 보는 것 뿐이에요, 그냥. 그러면 feasible 파티션은 의미가 별로 없고 의미가 없다는 게 아니라 이 정보보다는 efficient 파티션을 가지는 게 충분하다고요. 왜? 맥시멈 몇 개 들어가는 것만 알면 그 밑으로 들어가는 건 그냥 다 나오니까. 그래서 결국 efficient 파티션이라는 이 맥시멈 몇 개 들어가느냐 결국 이건 뭔가 하면 이런 거예요. 이게 A 쪽으로 하나도 안 들어가고 박스가 전부 돌렸을 때 B 쪽으로 박스가 몇 개 들어가는지, A를 옆으로 하나 놓고 다음에 B 쪽으로 박스가 몇 개 들어가는지 이런 식으로 주는 것뿐이에요. 그래서 84년에 결론이 뭐였는가 하면 이러한 박스 레이아웃 이런 것들은 전부 efficient 파티션만 우리가 알면 모든 걸 다 알 수 있다. 그거는 여러분들이 금방 증명을 해낼 수 있는 겁니다. 됐죠? 그래서 efficient 파티션이라는 게 이 모든 것들을 결정하기 때문에 그러면 우리가 뭘 할 수 있는가 하면 여기에 equivalence relation을 줄 수 있죠. 이것도 제가 준 건 아니고 이것도 이미 알려져 있는 겁니다. 그래서 어떤 식으로 주는가 하면 L 쪽에 efficient 파티션이 같으냐, 그다음에 with 쪽으로 같으냐, 두 개 같으면 그냥 같다고 보자. 이런 식으로 전부 다 처리하는 거예요. 그렇게 처리했을 때 우리가 보면 여기에서 나오는 것처럼 22, 16, 5, 3이나 30, 22, 7, 4나 이런 식으로 했던 세 개가 전부 다 동일한 파티션을 가지고 옵티멀 솔루션도 이 그림과 같이 동일한 것을 가지게 됩니다. 그러면 이제 생각하는 게 그럼 여기서 아주 좋은 레프레젠터티브는 뭘까? 이퀴벌런스 릴레이션 클래스에 그게 바로 MSI입니다. 뭔가 제일 작은 녀석을 고르자. 즉 A와 B와 L이나 W가 제일 작은 녀석을 고르자. 근데 이게 항상 존재합니다. 그런데 2014년에 이 사람들이 대충 이렇게 해서 O의 n 스퀘어 정도의 스피드로 알고리즘을, 그러니까 MSI를 계산해내는, 그러니까 레프레젠테티브를 찾는 알고리즘을 만들어냈어요. 근데 왜 제가 여기에 관심이 있었는가 하면 이 논문을 보기 전에 저도 이걸 만들었거든요. 그만큼 쉬운 거라고요. 그래서 이제부터는 제 이야기입니다. 7분 남은 동안 제 이야기를 전부 다 해야 되는데. 자, efficient partition은 아까처럼 그렇게 보여지지만 어떻게 보면 결국은 순서 시퀀스를 그냥 잡으면 되는 거예요. 그러니까 0이었을 때 P0 나오는 거, 1이었을 때 P1 나오는 것들을 쭉 잡으면 strictly decreasing 하는 시퀀스를 그냥 만들어낼 수 있다. efficient는. 그래서 아까처럼 이렇게 나오는 거는 이런 식으로 간단하게 7로 4, 2, 0만 가지고 오면 된다. 저걸 그래서 efficient partition이라고 하자. 그러면 제일 먼저 생각나는 게 이거겠죠. 임의에 strictly decreasing 하는 시퀀스가 있으면 이게 정말 저런 식으로 해서 efficient partition이 될까 안 될까? 제일 첫 번째 문제가. 그걸 이 사람들이 어떻게 했는가 하면, 뭘 도입했는가 하면 2014년에 ERI라는 Equivalence Ratio Interval이라는 저 LP, UP 이렇게 해서 계산하는 식을 만들어냈어요. 이건 저도 만들어낼 수 있는 만큼 학부학생 정도면 충분히 만들 수 있는. 그래서 오픈 인터벌을 만들어냈다고요. 이 오픈 인터벌에 B분의 A가 들어있기만 하면 이건 아까 봤던 efficient partition이 된다는 거예요. 아주 이거는 생각보다 어렵지 않은 겁니다. 그래서 아까 봤던 이그램플을 보면 대충 이런 거예요. 75420일 때는 그 오픈 인터벌이 2분의 3과 2이고, 그래서 이걸 우리가 기울기이기 때문에 B분의 A 기울기로 이렇게 보면 이런 식이고, 밑에 거는 이런 식으로. 이거고 이거 이런 식으로. 그럼 MSI는 뭔가? 제일 작은 녀석이니까 이 오픈 인터벌이에요. 그러니까 이 안에 들어있는 제일 작은 AB 포인트를 찾아내는 거예요. 이게 첫 번째 목적이었는 거예요. 자, 5분이니까. 그럼 제가 이제 관심 있었던 거는 이거는 이제 그 사람들의 세팅이었고, 이제 수학적으로 돌아왔을 때 임의의 strictly decreasing 시퀀스가 있었을 때 이걸 이제 ERI 아까 같은 오픈 인터벌을 계산할 수 있어요. 모든 strictly decreasing 시퀀스는 저런 식으로 오픈 인터벌 아까 식에 의해서 계산할 수 있는데, 이게 non-empty면 우리가 어떤 efficient partition이 있는 거니까, 그래서 그런 것들을 PLT 시퀀스라고 하자고요. 그러면 이제 딱 궁금한 게 이게 얼마나 많을까? 이뉴머레이션 하고 싶은 거예요. 그래서 보면 저 위에 PN, P0라고 적혀있는 게 뭔가 하면, P0는 임의의 strictly decreasing 시퀀스가 있을 때 제일 첫 번째 나타나는 P0. 그다음 N은 길이. 저런 거에 의해서 도대체 저 셋을 전부 모든 PLT 시퀀스를 담아하는 셋이라고 했을 때 저거의 크기가 어느 정도 될까요? 근데 우리가 잘 알다시피 strictly decreasing 시퀀스만 봤을 때는 결국은 그 크기는 바이노미얼 코에피션트잖아요. 그럼 이거하고 비슷한 형태가 나타나지 않을까 싶어서 보는 거죠. 그래서 뭘 해봤느냐? n이 0부터 p0까지 나타날 때 이걸 전부 썸을 해보자는 거예요. 즉 이거는 무한히 많은 PLT 시퀀스가 있는데 그 중에서 p0로 시작하는 PLT 시퀀스를 다 한번 모아보자는 거예요. n의 길이를 전부 다 뭐죠? 길이는 0에서부터 p0까지 하면서 strictly decreasing이니까 저게 나오겠죠. 저걸 다 썸을 해가지고 컴퓨터로 열심히 돌려봤죠. 얼마나 나오는가. 그래서 1, 2, 4, 7 이런 식으로 쭉 해서 50까지 한번 해봤다고요. 대충 어떻게 보면 바이노미얼 코에피션트를 생각하면 2의 50승까지 계산했다고 생각하시면 돼요. 해봤는데 이걸 당연히 인사이클로피디아 오브 인티저 시퀀스에 집어넣어 보니까 찾았어요. 50개가 같아요. 50개가. 무슨 식과? 이 식과. 정확하게 여기 있는 거지만 제가 그냥 2분의 1만 붙이면 되더라고. 29. 뭐가 쓰였는가 하면 오일러 펑션 이거 하나만 써 있는 거예요. 이 엄청나게 간단한 스트럭처가 나온다는, 만약에 이게 맞다면 엄청나게 간단한 게 나오는데 세상에 50개나 같은 게 이거는 우연치고는 너무 세다. 이게 어떻게 보면 출발점이었습니다. 그래서 제 물음이 이걸 이제 해보려고, 그래서 뭘 냈는가 하면 2분 동안 이제 다 설명을 해야 되는데, 이렇게 생긴 P0로부터 시작하는 모든 파티션, 그러니까 그 시퀀스들을 쪼개는 거예요. 뭐 어떻게 쪼개는가 하면 P0에서 시작해서 PN으로 끝나는 녀석들을 또 쪼개는 거예요. 이렇게 다 쪼개가지고 보니까 리덕션 시어렘을 제가 좀 발견할 수 있었습니다. 그래서 뭘 얻었느냐, 이런 식으로. 결국 저 녀석은 썸은 이렇게 썸을 하는데 끝이 0으로 끝나거나 끝이 1로 끝나는 그런 녀석들의 썸으로 다 리덕션을 시킬 수 있다를 얻었고, 또 열심히 리덕션을 해가지고 뭘 얻었는가 하면 이제 본격적으로 1분 만에 이 시퀀스를, PLT 시퀀스를 다 생각할 필요 없다. 바이너리 시퀀스만 생각하면 된다는 걸 얻어냈어요. 그래서 어떤 식인가 하면 어떤 0, 1로만 주어진 바이너리 시퀀스가 똑같이 우리가 이게 PLT 시퀀스인지 아닌지 데피니션을 만들 수 있었습니다. 데피니션을 만들 수 있었다고요. 똑같이 ERI를 계산하는데 어떻게 계산하는가 하면 이런 식으로. 아주 쉬워요. 바이너리 시퀀스가 있을 때 그 녀석의 서브 시퀀스들을 전부 다 생각하는 건데, 그 서브 시퀀스에 1이 몇 개 들어있는지 썸. 그래서 더하기 빼기 한 거, 그걸 서브 시퀀스의 개수로 나눠주는 정도 수준. 아주 간단한, 어떻게 틀림없이 이 식은 어딘가에 있을 것 같아요. 어딘가에. 너무 간단하기 때문에. 그래서 이 식과 아까 봤던 PLT 시퀀스의 ERI가 동일하다는 것을 얻어냈습니다. 이런 식으로. if and only if라는 걸. PLT 시퀀스의 if and only if가 이런 바이너리 시퀀스예요. 그래서 결국은 메인 테어렘을 우리가 리프레이즈하면 바이너리 시퀀스의 그 개수만 얻을 수 있으면 다 얻을 수 있다를 얻어냈다고요. 그래서 나머지 일들은 요게 어떻게 나올까를 이제 계산하는 건데, 하다가 이건 내가 할 일이 아니다. 이건 틀림없이 좋아하는 사람한테 물어보면 알 것 같다. 근데 이걸 어떻게 설명할 방법이 없다. 코로나 때문에. 그런데 워크숍을 한대요. 야, 이건 절호의 찬스다. 그래서 혹시 여기에 관심 있으신 분들은 저하고 이야기해서 콜라보레이터로 같이 일을 좀 하실 수도 있고, 생각보다 간단하기 때문에 여러분들의 아이디어가 그대로 가지고 있을 수도 있습니다. 필요하시면 제가 모든 정보를 다 드릴 테니까 저에게 이야기해 주시기 바랍니다. 이상입니다.
Are there any questions?
아직 그 문제는 증명하신 건 아닌 거죠? 아까 그 시퀀스가 같다 이거.
아니, 그 시퀀스를 같다는 걸 증명하기 위해서는 이걸 계산을 해야 되는데, 이 계산조차도 다시 여기에 이제 딱 걸려 있으니까 이걸 한다고 해서 그게 맞다, 그 증명이 된다는 보장은 없어요. 그런데 그 출발점이 세상에 50개나 갔다는 게, 이거는 우연도 이 정도 우연은 잘했다. 뭔가 이 복잡한 뭐가 어떻게 상쇄돼가지고 나오는 뭔가 있을 거야. 그게 이제
질문 더 있으신가요? Any other questions? Not, that's time for. And our final speaker is Professor Lee from Kyung University, and he will talk about detecting and recovering both manipulation produced X11.
First, 들리시나요? 네. 네. First, thank organizers for giving me a chance to give a talk. This talk is about some social issue, so detecting and recovering vote manipulation on ProduceX 101. So this is joint work with Taejong Park and Hyunju Song. They are professors at Deokseong Women's University, which is my previous university, and they are at CS department. So this result is about 3 areas. So first, the problem is from social issue, and okay, and firstly, I tried to solve the problem with mathematics. So I got some algorithm, and then we also used computer science. So we improved the algorithm, and also we considered how to evaluate the algorithm. So it was very fun project. So outline is the following. First, let me give you the motivation from ProduceX 101. And then let me introduce the mathematical question. And then let me give you 2 results. The first one is about mathematical results. The second one is about experimental results. And finally, let me give you a conclusion. And let me say something about some exclusive fact by revisiting ProduceX 101 series. Okay, so first, let me start the motivation, ProduceX 101. ProduceX 101 series was a survivor reality TV show in which the public produced a girl group or a boy group by choosing members with votes. So there were 4 seasons. In the first season, the girl group IOI was produced. And in the second season, the boy group 101 was produced. And in the third season, IS1. And in the fourth season, X1 was produced. And the problem happens here. So for each season, there are 4 main votes. And the problem happened here. So season 4, the last vote. So someone suspected that the final votes, the number of votes, have some weird patterns. So something is wrong. Something could be manipulated. So that's the starting of the story. So this is the final vote information about the season 4 and 4th vote. This is ranking, and these are names of candidates. And this is the final vote, the number of votes. If you see this number, you can see some weird patterns, like 444, 466, 4400, 4455, something like that. So that same 2-digit happens a lot, so it's kind of weird. And more than that, if we check the differences of the number of votes between candidates, more weird thing happens. So you can see many same numbers, like 29978 or 7494, something like that. So someone suspected this is weird, and I guess he used Excel to deal with this situation, and he figured out this kind of thing. So there are some small integers like this, 178, 174, etc. And then we can multiply some common real number, 7494.442. And then we can get this kind of number. But of course, this is a real number, not integer, right? So if we take a round function, then we can have this kind of numbers. And this number is exactly the same as the final vault. So yeah, maybe this is manipulated, right? So that's the story. So I heard this story 2 years ago, so 2019, November, December. So I had some mathematical questions from this situation. So first, let me address a mathematical question. So first, we let y1 through yn be ballot count from a vote. So this is final number of votes. And without loss of generality, we think that this is increasing. First question is the following. Can we determine whether the ballot count yi were obtained from some original data xi, integer data xi, by multiplying a large constant alpha? So I would like to do that automatically, not by using Excel for each yi data. And second question is the following. Can you recover x1 through xn and alpha if they exist? The last question is important. If it happens, if we can get this kind of numbers, xi and alpha, then is it random or modified? That's important, right? So it could happen randomly, right? So this is the main question. So this is the overview. So suppose that there are some original integer data xi, and we multiply some large constant vector alpha 0, and then we take the round function, and we will have an integer yi that is this number. And suppose that we hide this part, just we know this one, these numbers. We have no idea about xi or alpha 0. When we have these yi's, can we do recovering process? That's my question. So can we find, there exists alpha and zi such that yi is round function of alpha zi, so same function, right? And there are zi's, right? So of course, if this is manipulated from xi, this xi will be one solution of zi, right? But there might be another solution, right? So this is the process we want to do. Actually, this problem is just about multiplication around function. So one may think this problem is very easy to solve, but I think it's not so easy to solve. First, so let me mention why it's not easy. First, so we want to solve this problem within a finite number of operations, but this candidate alpha, the number of candidates alpha is infinitely many because alpha could be any real number. Also, we can consider some equivalent problem like this. So when we have yi, then we can get some candidates for the zi, like yi over alpha and round function, then we can get zi. Then we can define this kind of function, d alpha, as sum of difference between yi and round function of alpha zi. And if d alpha is 0, then that alpha is the correct one, correct multiplicative factor. So our question is whether we want to find all alpha such that d alpha is 0. But there is no viable solution on this problem in the literature, as far as I know. So it's not easy. So also when we check the function d alpha. D alpha is not unimodal and has many local minima and maxima due to two round functions. So when we go back to problem here, there is a round function here and also another round function here. So combination of two round function makes some complicated function. And secondly, one may consider brute force search by search some possible alphas, but it's not a good idea because interval of proper alpha could exist within very small interval. So if we take a small step size when we use brute force search, then we can't find an alpha, even though that there exists something. So this problem is kind of not trivial. So our goal is to propose an algorithm to detect all alpha with d alpha is 0 within a finite number of operations. That's our goal. Okay, so let me formally define the problem. Alpha is a real number. X1 through xn are non-negative integers representing genuine data before multiplication. And first we take alpha times xi, that is yi tilde. Yi tilde is a real number. Then if we take a round function, the yi will be the manipulated final number of votes. So yi are presented to the public as a voting result. Okay, then let me define proper multiplicative factors. A real number alpha is called a proper multiplicative factor with respect to yi if there exist integers zi such that yi is round of alpha zi. So as I said before, when we only know this yi, we want to find this kind of alpha with some proper zi. That alpha is called proper one. Then the proper multiplicative factors are not unique because you can easily guess that if alpha is a proper one, very similar number could be a proper one. So actually the answer for the set of all proper alpha is about union of narrow intervals around the proper alpha. And secondly, if alpha is proper, then alpha over 2 and alpha over 3, alpha over 4, etc. should be another proper one. So we want to find a proper vector alpha that is as large as possible. Then let me mention mathematical results. So theorem is the following. Let y1 through yn be non-negative integers that are ballot count given to all candidates from a vote. There exists an algorithm, so we made an algorithm that returns all proper multiplicative vectors alpha with respect to the given yi if they exist with a finite number of operations. So, and actually we want to find the largest proper one, so we can just return rightmost interval. Actually, based on the time limit, I can't say you about what is the algorithm and proof. But so if I just show you the algorithm is like this, so not so long, right? So yes, so this is it, but I'm sorry, because of the time limit, I can't say the details. So the algorithm detects election fraud by multiplication. So first, there are two cases. First, if yi are generated by a multiplication process with a specific multiplicative vector alpha 0, then the algorithm always returns on an interval. And the interval contains the correct multiplicative vector alpha 0 with a high probability. So we check this by experimental data set. Secondly, if yi are randomly chosen from a uniform probabilistic space, then the algorithm does not return an interval. So the algorithm returns that there is no proper one with a high probability. So when we have information, when we have numbers of yi, if we plug in the numbers in our algorithm, with a high probability, we can understand that that is manipulated or not. Okay. So let me explain experimental result. So in order to evaluate the algorithm, so we made a lot of data sets, and we plugged in the data set in the algorithm. So first, we prepared 20,000 multiplied data sets and the corresponding 20,000 unmultiplied ones as a control group, in Korean, 대조군. And the data, and we considered some important parameters, and we fit the parameters with respect to the produce X101. So let me say briefly this one. So n is the number of candidates, and xi, when we have x1 through xn, the lower bound of x1 is important, and the upper bound of xi is important. So we made 20,000 data set with some rule. So let me define some concepts. The first one is about actually multiplied or actually unmultiplied. So a voting data set yi is called actually multiplied if yi is generated by multiplication. Secondly, a voting data set yi is called actually unmultiplied if yi is generated without multiplications. And also, we have a concept about predictively multiplied or unmultiplied. This is determined by the returns of the algorithm, right? So the actually means it was generated by manipulation or randomly. And second one is about the result based on our algorithm. So let me skip it. So this is our experimental result. So this row is about actually multiplied, actually unmultiplied. And this is about predictively multiplied and unmultiplied. When we tried 40,000 data set, 20,000 each, so our algorithm is quite precise because for actually multiplied one, so manipulated one, 99% is true. And for random one, 82% is true. Okay, quite good. And also we considered condition on alpha. So when alpha is bigger, we guess that this is, our result is quite precise. So we considered the parameter alpha, the multiplicative vector. So this graph is about probability of wrong predictions vs alpha. So if alpha is bigger and bigger, the probability of wrong predictions is rapidly decreasing. So for example, if alpha is at least 6, then for actually multiplied data set, we are sure with 100%. And if alpha is greater than or equal to 16, our algorithm is 100% sure for both cases. So let me recall the produce X101 case. In the case, the alpha was what? 7,000 something, right? Right? So, right, yeah. So it means that alpha is quite large, right? Much, much larger than 16. So the result is quite sure, right? That was manipulated. Also, there are another conditions on n, the number of candidates. And if the number of candidates is increasing, then the probability of wrong answer is decreasing rapidly also. So for example, if n is at least 20, so the correct probability is like 100% and 99%. So if you recall the Produce X 101, so there were 20 candidates. So this is another good data. So also we can assume both of them simultaneously. And there are other conditions, but let me skip that based on the time limit. So conclusion is that, we obtained the algorithm. So if you have the final number of votes, y1 through yn, if you just plug in the numbers, then we can easily check that this kind of manipulation is done or not, and with a high probability, right? So when alpha is bigger or n is bigger. Okay. So let me skip it based on the time limit. And I had some question revisiting Produce 101 series. Until now, we considered this one, right? The last vote. So my question was about the other 15 votes, right? So that are manipulated or not. And we have algorithm, and we coded it, so just we can plug in the numbers, then we can easily check whether they are manipulated or not. So this is the result. So first is for season 4, this is multiplied, non-multiplied, and this gives the number like this. So the proper constant, so multiplicative factor is between this and this number. And that's the number in the previous page from someone, right? Okay, and about Produce season 3, we got another one, surprisingly, right? So multiplied here, and the number, multiplicative factor is 445. And do you remember? So if alpha is bigger, greater than or equal to 16, then this is for sure, right? So after I found this one, I checked the internet, whether nobody knows this or not. But someone already know this one. Okay. So let's move to Produce X season 2. Then I found another one. So Produce season 2, the last vote. And the constant factor was 3.9 something. So it's in a gray area, right? Because alpha is not so big. So, but yeah, so we are not sure about whether this is multiplied or not, but we may suspect, right? So this is the result. So it was really a nice project for me. So I got a mathematical problem from social issue, and also I used computer science to deal with that kind of algorithm. But there was another problem. What journal should I try? Right? Yeah. First, I tried this part, social issue. So I tried some kind of political journals or social journals. And I had some kind of dream to accept a paper at SSCI journal. But actually, that was rejected because actually they studied that kind of thing, vote manipulation. But their answer is like, yeah, this topic is interesting, but too much mathematics. so that was rejected. And secondly, I tried mathematics journals. But yeah, actually for them, for mathematicians, this problem is first about some multiplication around the function. So it's like not so deep, right? And also there is no this kind of problem before in literature, right? So I also got rejected. But so last I tried the computer science journal, and it was accepted at a good journal at computer science area, IEEE access. So I'm now very happy to have a paper. Okay. Thank you for your attention.
Are there any questions?
So is there any big change if you change the round function to the float function, then it works something different?
It's not so different, I guess. So just we can change the algorithm of it, and we can also check that kind of thing. Or scaling function.
Any other question?
If the manipulated data is a little bit perturbed by random things, then can he still detect this?
Oh. Yes. I didn't try it, but it depends on the size of perturbation. So if that is very small, you can detect it. If that is a bit larger, then it seems like a bit random thing. So yeah, it should be studied